Hello guys, welcome to Backbencher Studies channel. Today we are learning about the stability based on transfer function. In the last video we discussed how the stability affects the system, why it is very much required in control system. So let us start our session stability based on transfer function. We have the transfer function in Laplacian domain as like this: g of s is equal to some polynomial in s and some polynomial denominator polynomial in s as well with corresponding coefficients. So we can write the polynomial as roots like this, just like that. So the roots of the denominator polynomial are zeros. So with coefficient bm here, so we have the numerator polynomial of the transfer function as the product of the roots of this kind, and we can write the denominator polynomial as well in terms of the poles. So if we apply the partial fraction technique and thereby solving or thereby finding out the output corresponding to a given input, this transfer function is the ratio of output to input. So remember that this transfer function is nothing but C of s over R of s. So in this way the transfer function is directly proportional to the output C of s of the system. So if this transfer function is is made in this form by using the partial fraction expansions, all of these p1 p2 or pn are, when all of them are distinct, then we can write these as, we can express this transfer function as like this, like a1 by s plus p1, a2 by s plus p2, so similar like that. So if we kind of take the inverse Laplace transform for that, so we have the exponential of at Laplace transform as 1 by s minus a, and exponential of minus at Laplace transform as 1 by s plus a. So this is kind of 1 by s plus a. So we have the exponential minus term like that. So if, by this, if we say that if we have 1 by s plus p like that, so s plus something, then we have the exponential of minus terms in our output equation and in our transfer function as well in time domain. So thus we can say that the system will be bounded output, because for every bounded input it should lead to a bounded output. So whenever by taking that poles, real parts of these poles are less than zero, then we can say that the system will yield Beaver stability. So in this way, we can kind of summarize the whole thing as a system with poles in left half of S plane is stable, or the these poles may be an imaginary number. So this poles having an imaginary number is having a real part of it. So if this real part is less than zero, or if this real part is negative, then we can have something which is exponentially decaying function, with thereby yielding us a stability. So if this p1 is a complex number, and if we do that, then if we do this analysis based on the inverse Laplace transform, then we can have this kind of expression over here. So this exponential with the real term is an exponentially increasing or exponentially decreasing based on this polarity of this a. and this e power minus j beta is an sinusoidal variation, complex sinusoidal variation. So thus we can say if a is greater than 0, then we have the exponentially increasing kind of output pattern which is unbounded, which is not required, which makes the system unstable. And if this a is less than 0, what is a? A is the real part of this pole. If this a is less than 0, then we can have the system as bounded because it is exponentially decaying sinusoids. So this is how we can arrive at this conclusion. So if there are real poles on imaginary axis, then it can be said that it is marginally stable. So consider an S-plane, we have poles on left half of S-plane, then that will make the stable, and we have the right half of S-plane as unstable region. In between that, we have marginally stable region. So a imaginary axis, if there are poles, then that will be marginally stable. However, if there are repeated roots, then it will become unbounded. So because if we see these are the imaginary, these are the imaginary roots which are repeated at plus minus j omega over here. So if we kind of apply the inverse Laplace transform, for that we can have a function with constant multiplied over here and this r of t, because the Laplace of r of t is 1 by s square kind of thing. And if we uh, do this time shifting property, then we can have a similar kind of function. So this will be an ramp signal which is unbounded actually. So this is how a repeated roots on the imaginary axis makes the system unstable. So to summarize what we have learned, if there is if the real part of the pole is negative, that is the sigma is negative, then we can say that system is stable. And this is the unstable region, the right half plane of this S plane, and this is kind of marginally stable, this imaginary line. If there are imaginary repeated roots, then that will be unstable. So let us solve some problems regarding the stability and location of poles. So for first, let us see this. So here is one pole over here and one pole over here and one pole over here. Complex conjugate poles are here. So if we see that this pole is in the left half plane and these three poles are in the left half plane. So this system is stable. And if we see this one, second one, we have two poles in left half plane and three poles on imaginary axis. So there is one pole on imaginary axis, then that will be marginally or critically stable. So this is a critically stable system. So if we see this, so we have two poles on the left half plane and two poles repeatedly on the imaginary axis as well. So if this is repeated poles are there on imaginary axis, then that will be stable. We saw that because it is leading to a ramp signal, just like that, just like that. So this is how we can find whether the system is stable or unstable based on the location of poles in S plane. So that's all for today, guys. If you are watching this channel or this video just before your exam, please do like this video. You are a real backbencher. Thank you, guys.